In this lecture, I would continue to talk about the general big topic, which is fast Fourier transform. And in particularly, I would like to discuss with you how to figure out the value of p, the power p, that you have to raise w raised to the power p. How do we figure out the power p in this particular lecture? Okay, according to the previous lecture, we know that, let's say we want to compute at level L the intermediate vector f sub L. We want to compute the vector f sub L corresponding to level L. Now, when you want to compute the vector f sub L at level L, there are 16 nodes that you need to compute, 16 number that you need to compute based on the index k. Now, remember for the example where capital N is equal to 16 data point, that when n equal to 16 data point, n equal to 16 data point, that corresponding to 2 to the power r. That means r must be equal to 4. So when n equal to 16 data point, the index k that you have, the index k, should go from 0, 1, 2, all the way to 15. So you have 16 number to calculate. And depending on the specific value of k, remember k could be anywhere from 0 to 15 in this example. Depending on a specific value of k, the power p will be different. So the question is, for a different value of k, how do we compute the power p? Now, you also recall that I told you many times earlier, if you compute, let's say, the value of FLK, node k always have a companion node, and the companion node of node k is given by the expression inside that parenthesis. So basically, we always say the companion node of node k is equal to node k plus the distance n divided by 2 over L. Okay, so that means the so-called node k and node k plus n divided by 2 to the power L, we call they are two companion node. Two companion node. Now, these two companion nodes, the computation, if you can see, are very, very similar. Because, for example, if you look at the first equation here to compute FLK, and you compare that with the second equation to compare the companion node FL of k plus n divided by 2 to the power L. If you compare the right hand side of those two equations, they are essentially, the computation of these two companion nodes are the same. The only thing different is, instead of plus the product of w raised to power p times f in the previous vector L minus 1, now in the second equation you have a minus sign. That is the only thing different between the computation of the two companion nodes. So, like I told you, the main objective of this chapter or of this lecture is corresponding to a certain value of k, the index k. How do we find out the value of the power p? So let's take a look at a specific example. Suppose we say I want to compute corresponding to the index k is equal to 8. I want to compute, let's say, the value of k corresponding to the index k is equal to 8. Now, what does that mean? Well, let's say when k is equal to 8, the index k equal to 8, the index k equal to 8, how do we figure out the value of p should be equal to how much? Well, the way to figure out the value of p is rather complicated, and let me try my best to explain to you. First of all, for k equal to 8, we can express the value 8 by using r bits. Well, in this particular case, because r is equal to 4, that means we can express the value of k equal to 8 by using 4 bits. R equal to 4 bit. So we can say 8 is the same thing as 1, 0, 0, 0. In other words, we express the value 8 using binary form with r bits or 4 bits. Now, when I say binary form, what I mean is the value can be either equal to 0 or 1. That's why, and also you have 4 bit. That's why you have 4 number here. 1, 0, 0, 0. Now, we all know the binary number with 4 bit, 1, 0, 0, 0, corresponding to this number 0 in here, the last 0, will corresponding to 2 times 2 to the power 0. And then this number 0 in here, next to the last one, will corresponding to 0 times 2 to the power 1. The next number 0 will corresponding to 0 times 2 to the power 2. And finally, the number 1 in here, in the binary form, corresponding to 1 times 2 to the power 3. So you can see 1, 0, 0, 0 in binary form is the same thing as 1 times 2 raised to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 plus 0 times 2 to the power 0. That is exactly equal to 8. This value is equal to 8. So, to make the story short, any index k that you want to compute, let's say k equal to 8, we can express that in the binary form using r bits. So in this case, 8 is the same thing as 1, 0, 0, 0. Okay. The next step, which I call step number 2, we slide this binary number into r minus l position to the right. Now, what does that mean? What I mean is, remember number 8 can be represented as 1, 0, 0, 0 on the binary form. Now, if we slide this number to by r minus l position, well, in this example, r is equal to 4. Capital L is the level, let's say is equal to level 2, because if you look on the previous slides, we assume k equal to 8, level equal to 2, r equal to 4, and n equal to 16. Okay? So after we get the binary number 1, 0, 0, 0, with corresponding to the value of 8, we slide that one to r minus l, which is equal to 2, position to the right. So when you slide it to the right, the binary number 1, 0, 0, 0 will become something x, 1, 0, comma, 0, comma, 0. Okay? So, and then after you slide it by 2 position to the right, like what I just showed to you, you fill in those things that I said with the x, you fill in with the 0. So let's say 0 here, put a 0 here. So after you slide by 2 position to the right, the number 1000 will now become 0010, which I said in here. So, but that number 0010 will corresponding to the value of 2. Why? Well, you all know, I just explained to you in the previous slide, this number 0 in here mean 0 times 2 to the power 0. This number 1 in here basically mean 1 times 2 to the power 1. That number 0 here mean 0 times 2 to the power 2. And this number 0 here mean 0 times 2 to the power 3. And therefore, if you add up this number, which is 0, plus this number, which is 2, plus this number, which is 0, plus this number, which is 0, then you get the value of 2. So, to make the story short, from the step 1, 8, the value k equal to 8. In step number 1, we express 8 in terms of the binary form, like 1, 0, 0, 0. Then in step number 2, you slide this number, the binary number, to the right by 2 positions. And then you fill in with a bunch of 0, correspond to the one that we say XX. Then that binary number 1000 will become 0010. And that 0010 in the binary form, meaning it have the value equal to 2. Well, that value of 2 actually can be considered as the value m divided by the formula which say k divided by 2 raised to the power r minus l. Why? Well, k is equal to 8. You can see that k equal to 8. R is equal to 4 because you have capital N equal to 16, which is the same thing as 2 to the power 4. So R equal to 4. L is level 2 for this specific case, like I told you earlier, L equal to 2. And therefore, the value 2 is the same thing as the value m divided by that formula, which is k divided by 2 raised to the power r minus l. Okay, so that is step number 2. Step number 2, right now we got the value of m, which is the same thing like 0, 0, 1, 0. Step number 3, we